Hi, welcome back to my channel. Well, in this video, we'll try to learn a very important algebraic procedure which plays a very significant role in testing of hypotheses, especially in testing the homogeneity of several means. So that algebraic procedure is known as analysis of variance. So let us proceed. As far as group comparisons are concerned, we are always interested to seek the comparison among groups in terms of means or in terms of variances. So when we are interested to test the homogeneity of two samples in terms of means, we prefer t-test, but the question is when we have to test the homogeneity of more than two groups or more than two samples in terms of means, what we are going to do. So we shall be having an extension of t-test. So the question is, do we have an extension of t-test? Yes, we have an extension of t-test. That is known as analysis of variance, which is used to compare or to test the homogeneity of more than three groups in terms of means. Actually, it assesses whether there exists a statistical significant difference among different groups in terms of mean. Using analysis of variance instead of multiple t-tests also helps to control type 1 error, which is nothing that the probability of committing, we can say, the probability of making at least one type error in multiple comparison. It is more efficient and provides more comprehensive analysis when dealing with multiple groups. So as far as the historical background of this analysis of variance is concerned, the credit goes to the father of statistics, Sir Ronald A. Fisher, a famous British statistician, evolutionary biologist, we can say, is credited with the discovery or invention of this wonderful algebraic procedure in his famous book, which was written in 1921, entitled Studies in Crop Variations. Now, this analysis of variance, or ANOVA, is a statistical procedure, or we can say an algebraic procedure or a statistical method used to compare means of three or more groups to determine if there is a statistically significant difference between them, or we can say whether there exists a significant difference among different groups in terms of means, whether the difference among the groups is real or it is by chance or by error. It also assesses whether the variability within group is similar to the variability between groups. That means ANOVA calculates an F-test, so which represents the ratio of variability between the groups to the variability within groups. So actually it decomposes the overall variation into two components. One is assignable cause and another one is non-assignable cause. So one is due to the inherent variation which exists among the different groups which we are comparing, and another one is due to the error or due to the non-assignable cause or extraneous factors which are not in our control. Then those two variances are authenticated by means of this variance ratio test that is known as F-test. So F-test plays a very important role in analysis of variance. So we have different types of analysis of variance. If we are comparing different groups based on a single dependent variable or a single factor, that can be done by means of one-way ANOVA. And if we are examining the influence of various independent variables or factors on a response variable, that comes under the category of two-way. Or if we are interested to analyze the interaction between various multiple factors simultaneously in a single experiment or one response variable, then that comes under the category of factorials. The example of one-way ANOVA is, for example, if you are comparing the effectiveness of different pesticides on crop yield, so you want to see whether there exists a significant difference among different objects of comparison with respect to a variable of interest. In this scenario, a researcher wants to compare the effectiveness of three different pesticides to the three different groups or three different objects of comparison of three pesticides A, B, C, and controlling a specific pest that affects the crop yield, such as effects on the tomato. So such kind of scenario comes under the category of one-way ANOVA. And if we are interested to see the combined effect of two factors, say for example assessing the impact of fertilizer type and soil, where this fertilizer type have got two levels, organic and synthetic, and soil pH is neutral or acidic. So whenever we are interested to seek the combined effect of two factors simultaneously in a single experiment, that can be done by means of two-way ANOVA. Now various assumptions are involved because F-test plays a very important role to test the authenticity of the two group variations, whether the variations are real, or whether there is an extent of homogeneity of variance, or whether the groups are homogeneous in terms of means, or whether there is a significant difference among different groups in which we are interested. So the errors which play a very important role in this analysis of variance, they should be normally distributed, independently, identically distributed, or we used to write in this, errors tends to follow a normal distribution with zero mean and variance 1, which has already been discussed in a video which was made on probability distribution. The normality can be checked by means of pairwise test, and this homogeneity and non-existence of correlation can be checked by means of Bartlett's test or Levin's test, and this independence can be tested by means of Anderson's-Darling test. Since it is an algebraic procedure which decomposes this overall variation into two components, mean and within, and this F actually authenticates whether the contribution between variance is more or within variance is more. So by means of example, we'll try to elaborate it. For example, if we have three samples with their respective sample size and their values or average, and we have respective sample standard deviation with variances. So we have three samples here, and we want to seek whether there exists a significant difference among these three samples. So whenever we start a certain kind of an experiment, it always starts with a certain kind of hypothesis that is known as null hypothesis. So we assume A, B, C, all these samples are same. Now we have to apply the standard algebraic procedure and way to verify whether we are in a position to accept this null hypothesis or we are in a position to reject it. So the sample size is 3, or we have 3 samples, sample size is 5, and overall mean is 16, that is 12 plus 16, 20 is equal to 48. 48 divided by 3 is 16. So we have to get the variations first, then the variances. Since the variations in statistics are known as sum of squares and the variances are known as mean squares, so in order to get the variation due to these groups, that is summation n into x minus x bar, so we can simply get this 12 minus 16, 16 minus 16, and 20 minus 16, and 5 will remain constant because we have an equal sample size. So we will get 160 is our sum of squares due to these samples, or we can say the variation. Whenever the variation is divided by its respective degrees of freedom, and in this case we have s minus 1, that is 3 groups, minus 1 is 2, it becomes 80. So the mean square due to these treatments, or due to these objects of comparison, or due to sample, is 80. Now what we have to do is to get the mean square due to error, since we have to get the value of f. So mean square due to error, or sum of, first we need to get the variation due to errors, that is summation n minus 1 into the multiple of the sample variance, that is 4 multiplied by 4 plus 4 multiplied by 1, 4 multiplied by 16. In the first case, 4 is the variance of first group, 1 is the variance of second group, and 16 is the variance of the third group. And this 4 remains constant, it's not, it's n minus 1 for each and every group. That's 5 minus 1, 5 minus 1, and 5 minus 1. So 84 is a variation due to the errors, or we can say a non-assignable cause. And in order to get the mean square of the variance, we will divide this with its respective degrees of freedom. That's n minus s. N is 15 and s is 3. Why 15? Because we have 3 samples and every sample is based on a size of 5. So 3 multiplied by 5 is 15. 15 minus 3 is 12. So when we divide 44 by 12, so overall variance due to non-assignable cause or due to error is 7. So since the we have to use this F test or a variance ratio test to see whether there exists a significant difference among these 3 samples or not. So simply we will use substitute the mean square values of these two, calculated the variances, mean square due to treatments or mean square due to samples and mean square due to error. So 80 divided by 7 is 11.42. So this is our calculated F. So we have to compare this calculated with the critical or a tabulated value with 2 and 12 degrees of freedom, because of numerator has got 2 degrees of freedom, which is here, and this denominator has got a 12 degrees of freedom, which is here. at 5% level of significance, it is 3.88. And the thumb rule is whenever the calculated value of any test of significance is greater than its tabulated value, then we have to reject hypothesis, null hypothesis under this case. So we have got an evidence that all these three samples are significantly different from each other. That means there exists a significant difference, so the difference among them is real, it is not by chance. So this is the way we use to do this algebraic procedure, that is known as analysis of variance. This analysis of variance plays a very important role as far as the experimental designs are concerned. In a next video, we'll try to learn about the basic principles which are involved in experimental designs, and we will discuss one by one different single factor and factorial experimental designs in other videos. So hope you will like this video. Thank you very much.